I love breaking things. I always have. When I was a kid, I was fascinated by how things come apart and go back together again, like all my brother's toys. And as I've grown, so too has the scope of my interest, because now one of the key things that I study is how planets break. And it turns out we've got a great example of that very thing right under our feet. The outer shell of Earth is broken into pieces we call tectonic plates. And there's two kinds, oceanic and continental. Oceanic plates are formed in the center of our ocean basins, and they move outward, conveyor belt-like, until they ultimately meet and inevitably lose to the stronger and lighter continental plates. The oceanic plate dives under or subducts beneath the continental plate and is recycled back into the Earth's deep interior. Now, the longest this process takes anywhere on Earth is about 200 million years. That's an unfathomably long amount of time to someone like me who can't remember this morning. But relative to the age of the Earth, 4,500 million years, it's not a very long amount of time at all. Now, continental plates don't fare much better, because when they meet, they push up and they form long mountain belts. They get sheared, they deform, they end up not looking at all like they started out looking like. And when you combine the effects of erosion and vegetation and human activity with the recycling and resurfacing effect of plate tectonics, we find ourselves in a situation on Earth where we have ready access to only 5% of Earth's geological history. And if we want to understand how Earth formed, what it looked like in its early days when life crawled out of the oceans, or how it developed through time, that's a real problem. And that's where other planets come in. Of all the places that I've been so lucky to study in the last few years of my career, the giant volcanoes of Mars or the scorched surface of Mercury, I've been able to apply all the things that we know on Earth, the processes, and we understand how they work, to those other worlds, to understand the forces that shape those other worlds. This is a technique we call comparative planetology. Comparative planetology is a toolkit, essentially, with which we can use our own understanding of Earth. We look at other worlds through the lens of our own. But it's a two-way street, because comparative planetology offers us a mirror to look back on our own world by looking at the surfaces of these other planets. What drives plate tectonics is heat, and there doesn't seem to be enough energy in any other body in the solar system to break their outer shell and produce plate tectonics. So instead of their surfaces being resurfaced, being subsumed, they're still there, preserving, in some cases, a record of geological activity that stretches back to the earliest phases of solar system history. These planets offer us a glimpse of Earth in its earliest days. They offer us the capacity to ask the question of our own world: where did we come from, and where might we go? And I, for one, can think of no more important a question to seek to answer. Thank you.
What got you interested in this besides breaking your brother's toys? Why'd you get into planetary geology?
When I was that size, I had a map of the nine planets in the solar system. And I was just so fascinated in these alien worlds. One thing that I loved back then, watching Star Wars and Star Trek, something I try not to lose sight of now, especially at stuffy scientific conferences, is that we're looking at alien worlds. This is just like what I grew up reading about. And being able to share that is something that's incredible, both aged 5, being the geeky kid in the playground, and now standing on stage sharing this with you.
So you said that these other worlds like Mars and Mercury are have less heat, they're smaller, and so they can't break their plates as readily. So what about Venus?
A question, you figured you were going to ask that question. Venus is the freak, and here's a great thing. Venus is almost the same size as Earth. It's not our twin. There's something wrong with Venus, because the surface of Venus has the same temperature as a self-cleaning oven and the pressure of the bottom of the ocean, yet it's almost the same size. Why hasn't it followed the same trajectory our own world does? The oldest surface on Venus is about 800 million years, but it doesn't have plate tectonics. What's going on? We don't know the answer to that question. We don't know for certain that it might not have had plate tectonics early on in its life that somehow stopped. But crucially, all of Venus's atmosphere is carbon dioxide, an enormous concentration of it. We're pumping more carbon dioxide into our own atmosphere. The question is there going to come a point, a tipping point, when our own planet's trajectory will follow that of Venus? And that's the power of comparative planetology. It's not just understanding the past, it's seeing what might happen in the future.